Hello and welcome back to the development of the Feersum scheme compiler. So in the last stream we took a detour away from Feersum itself and did a bit of work on a library called Firethorn, which is an implementation of something called red-green syntax trees. But today we should be back on the Feersum compiler itself, trying to integrate that new library. The whole idea is that I want to rip out and replace the parser for Feersum, because although it does tolerate failures, it doesn't have a lossless representation of the source text, and some of the things that we want to do with manipulating the source, manipulating syntax trees for things like macros and that kind of thing, will be a little bit easier with the representation of syntax trees that Firethorn will give us. So I think the first thing to go over is just what we did last time in the Firethorn library. So that is here. So basically it's divided into, let's have a look at the README first. So the whole point of this library is that we have two layers, the red tree and the green tree. So the green tree is the base layer, and it looks a little bit like this. You have tokens and nodes. So tokens are the leaves and nodes are the interior nodes. And every token and node has a kind, and the kind is just a number. We don't have any like stronger representation of it at this level. And then every node has a list of children, which are either nodes or tokens. And then the individual tokens in the tree store the text. So we have all of the source text in here. And then so each one of those nodes in the tree, like 1 in this example up here, 1 and plus would be potentially nodes or tokens, but like the actual characters would be inside a token. So there'd be a token somewhere that has the 1 in, a token that has the space, a token that has a plus, a token that has the space, a token that has the 1. But because these tokens just know about how big they are, they don't know about where they sit in the tree, we can use the same instance of the space for this space and this space, and the same instance of the 1, both of the 1s. Then on top of that tree, we layer something called the red tree. So the red tree has it has tokens and nodes, where the tokens represent the leaves and wrap the individual syntax nodes, which it calls green nodes. Sorry, the green tokens, and then it has a pointer to its parent, or a reference, an option to its parent, and its absolute offset in the source file. And the same thing for the syntax nodes, where it has the absolute offset. And what happens here is, with the offset and then the width of the green node, you can work out the span of the whole syntax node in the tree. And the only way to create one of these red nodes is to start at a root and effectively walk through the children. So if we have a look at the red tree, it has the implementation of syntax node. We have create root. Whoops, that's a bit too much. Again. The implementation of create root just sets the parent to none, the offsets to 0, and wraps the underlying node. And when we want to get the range of a token, we do that by getting the start and the end, where the start is the current offset and the end is the offset plus the length of the green thing. So it's fairly simple to get a range out of the syntax node. We also have an iterator for children. Can I get this into the middle? Yeah. So the iterator for children uses a map fold to keep track of the current offset, and then every time we create a child node or a child token, we add on the length. so we keep track of how far through the source file we are. And this is how the syntax nodes and syntax tokens, the red parts of the tree, get their offsets. It's based on relative offsets from whatever their parent's offset was. So we basically always start at the root and work our way down, keeping track of how far through the file we've come. We've got a few helper methods like children, which basically just gives you all of the nodes. We've got custom implementation of equality, because syntax nodes are the same if they have the same parent, the same offset, and are wrapping the exact same green node. We don't need to worry about looking for actual structural equality of the green nodes here. So the green node could be arbitrarily big, and we'd still be able to tell that it's the same red node in fairly constant time, because the red nodes will always have been created from the same parent, and therefore they will always be wrapping the exact same object reference. The green token is similar but not quite as complex, because there's no children operator that we need to implement, but we still have implementation for the range. And then for each one of these layers, we also have these elements, which is just a type alias for this node or token. So node or token is I tried to go to the get definition there, and that did not work, because we're not actually in an F# file. Is that right? No, we were in an F# file. Red tree. Yeah. Oh, that's not good. It's in node or token. So the node or token is basically just a custom version of that choice. So we can have either a left hand or a right hand. In this case, we're calling them node and token. And we have a bunch of helper methods to filter down whether or not we've got nodes, tokens, map them. I'm not really sure about this consolidate, but I have not got a better idea for a name for that yet. And then these as node and as token functions that turn it into an option of the inner, which are very useful for when we want to come and build up syntax trees. So I guess the next place to go is if we have a look at the parser that we also wrote. So we have a parser here for a simplified syntax for lambda calculus. So in our parser, this is a bit of a hacky parser, but we have our token kind, which is like our strongly modeled kind for all of the tokens that we get from the source text, because Firethorn doesn't deal with any of the tokenization stuff. And then we have the AST kind, which is just like a numeric value for everything in the tree. And here we have like nodes and tokens are all part of the same enum. Then we have some functions helpers to convert between the different kinds. Our Lexer is very simple. It's just a for loop that goes over every character in the string and classifies it, so our tokens are only ever one character long. And then the parser itself has a few helper methods like get text, get kind, and current, bump, which are for working with the current tokens, and looking at helpers for working out whether or not the kind matches. But the actual meat of the parser is these functions: skip, whitespace, no new lines, expect, parse error, parse use, parse abstraction, blah, blah, blah. So each one of these represents a non-terminal in the grammar for the language. And for example, if we're talking about the parse abstraction, we call start node on this green node builder, which it means like, oh, we're going to enter into a syntax node of kind abstraction. Then we call expect. It says we should see a token, which is a lambda. And if we do see it, record record it into our green tree as AST cat and lambda. Then the same thing for identifier and then dot. So this means when I'm seeing an abstraction, which is something like this, an abstraction would look like backslash, which is what we're using to represent the lambda character here, x dot, and then some body. So like x dot x would be the identity function. So in this parser, we're just saying like I expect to see the lambda, I expect to see an identifier, I expect to see the dot, and then we recurse into this expression because we're then saying like I expect to see an expression which represents the body. So this could be anything. It could be another abstraction. So it could be like lambda y, x, y. And then, so basically this is a function. This is defining a function that returns a function which, when invoked, calls the first function with the second value as the argument. Which I think, is that just apply as a function? Something like that. Anyway. And then once we've finished building up a node at each level, we call finish nodes to complete it. So parse expression does something a little bit more complex because we store a mark. So a mark is a way of potentially coming back and starting a node at the same position without actually committing to do it. And then we match over whatever token we're currently looking at and use that to decide which of the productions we're going to call. So we also have this fallback for parse error, which ensures that the parser always makes some kind of progress, which is important to be able to do infallible parsing. And then there's a sprinkling of this skip whitespace and skip whitespace new line stuff to make sure that whenever we are writing these kinds of productions, these non-terminals like parse abstraction and stuff, we can just say I expect to see a lambda and then an ident and then a dot, but in reality I could have put whitespace like there or there and it would still be fine because the individual expect checks to make sure whether it's looking at a whitespace. It skips over whitespace before deciding whether or not you're looking at the correct kind of token. And the other thing to note here is that when we aren't looking at the thing that we expect to see, we add error tokens in. So when we have that parse error, we store it as a node in the tree of type error, which means that everything is in the tree somewhere. It's just it may not be what you expect it to be. Like it may be that we expected to see, if we go back to our abstraction example, if I did like lambda x, but instead I wrote like lambda x dot x, we'd end up with this in the tree, but it would be as an error token because although it is a lambda in terms of it, the underlying token that came back from the tokenizer, it wasn't what we expected in that production. So the lambdas, so the kinds of the tokens that we get back from the tokenizer, the Lexer, don't necessarily have to match up with how they end up being stored in the syntax tree. So that's the like simple parser that we wrote. Our AST module wraps the red tree. So in syntax token and syntax nodes are the elements in the red tree, and we have basically a bunch of different types for each one of our strongly modeled variants, which call cast, where cast just checks to see if it is the kind of node or token that we expect to see. And then depending on what they are, we might expose strongly typed properties. So like rather than you having to dig around in an untyped syntax tree for the identifier, we do children with tokens and pick the token out that is the identifier when we're looking at a use, for example, which is when you've referenced a variable. And when we're looking at an abstraction, you have the binding, which looks for the identifier. You have the body, which looks for the expression. And the same kind of thing for the remaining elements in the syntax tree. So like a program has a list of expressions. So the value of each one of these expressions or body or whatever is either an option or it is an enumeration. So expressions is a seek and body is an option. And that's because we're wrapping a syntax tree which could contain errors or missing nodes and all the rest of that kind of stuff. So you can never guarantee that any part of this is going to exist. So in the strongly typed part of it, we make sure we model that by just using option. So that's the simple part of the we wrote for the lambda calculus. I'm just going to have a cup of tea. So what's the plan for today? The plan for today is that we are going to look at changing out the parser in Feersum itself. So currently we're using fparsec, and fparsec is a parser combinator library. So the way that this works is if I go find syntax, we have a parse module. Well, we've got definitions for our AST state, but we have a parse module, and inside here we have a bunch of different functions. Try to look for one now. Like comment, which are of type parser. So everything above this I think is just a helper. So all of these functions that are of type parser are parsers. So they're capable of recognizing some specific language. So in this case, like WS, this is capable of recognizing the language of white space. And it does that by building up a parser based on several other ones. So it says it uses the combinators skip many and either to build up a parser that will parse any language represented by a repetition of a comment or a space. In this case, it says Unicode space is 1, which means you should see at least one space character. Because, I mean, you could say that no characters at all is white space, yeah, whatever. And the same thing for things like numbers, where it's in numbers, but the return value of each one of these is actually parser, which takes two type parameters. In this case, in comment, it's unit and state. This means it produces no value. State is our like parser state that gets passed through all of these, and we can mutate it, and we use that to build up our list of syntax errors. But yeah, I think that's it. The idea is that basically you build up parsers based on smaller parsers. So in case of here, comment actually has several different smaller parsers. It just has local variables here for things like block bodies, and then it produces a parser at the end, which is either a single line comment or a datum comment or a block comment. And this is great, and it's a really nice way of modeling out languages, but it kind of muddies the water in two ways. One is that like each one of these productions has a return value, which we've modeled up here as like the syntax constants and like syntax nodes, where the node has like a kind and a location. And this is all very great and very strongly modeled, but it doesn't necessarily deal with broken bits that well. We just basically end up with a bunch of nodes that are of kind error. Whereas it would be a little bit nicer if we had the node kind of be a form rather than an error or a sequence or quoted or whatever it's supposed to be, just with the individual broken bits missing. But we can't model that using our current types quite as well. And the other thing is that you lose the distinction between tokenization and parsing. So if we have a look at something like a comment, you'd expect if I was to write this in F sharp, like hello world, this thing here, you'd expect this to be a single token, which is a comment. But the way we're parsing it, like this is no different from like this, which would also be a token, but then it's also no different from the whole of the body of the method, which I would say is definitely a non-terminal in the grammar. There's like a separation between these terminals and non-terminals in how you match them, but it's often quite nice to think of things like white space and comments and identifiers and operators rather than when you're building a parser by hand, rather than having to think about it character by character. So I think the first thing that we want to tackle today is introducing a Lexer, which will recognize all of the different tokens that we need to recognize. So I guess the place to start here is that we can't just rip out syntax yet because it's kind of a load-bearing part of the whole infrastructure. So what I'm going to do is I'm going to create a new file, and we will call it syntax2, maybe. Well, how about we create a new folder called syntax, because we're going to split this parsing logic out into several different things. And we call this Lex for the time being. And just to clarify, we can split things out into, so that the current syntax is called like syntax old or something. Legacy syntax. And then we'll have we have our Lexer, and then in here we can just rename this to be legacy. I think we need to use rename file. Rename. Has that left a... Yeah, it has. How does one... Oh. Right. Guess we just have to manually delete it. And then our Lexer. So we need how is this going to work? So traditionally, the way that this kind of thing works is, he says, pausing while he brings in a blog post. Traditionally, the way that this thing works is that you have a grammar like this. So this says var is an alphabetic character followed by any number of, including 0, alphanumeric characters, for example. And a number is any number of numeric characters, and the operator plus is just the literal string plus, which is great. And what you do is you build a state machine for each one. So for example, in this case, we say to recognize plus, we start in the state 1, which is you can tell it's a start state because the state has one entry point and it comes from nowhere. And then if we recognize the plus, so in this case, the labels on the edges tell you what you need to see to move between the states. We go into state 2, and 2 has 2 lines around it because 2 is an accepting state. So that's a pretty simple state machine that says basically you start off not having seen a plus. If you see a plus, you're done. And if there's any transition that isn't in the state machine, you're effectively in an error state. For our numeric one, we say like if we haven't seen a number and we see a number, we move into state 2. And then if we continue to see numbers, we can move into state 2. And this basically means that we need to see at least one number, but any number after that. The one for variables is a little bit more complex. We need to see a letter. And then what we have here is this Epsilon transition, because we're going from the first part to the second part. So the Epsilon transition, you don't need to see anything to move along this. You can either stay here or move here. But basically what we're saying is that you see a letter, and then if you see a letter or a number, then you're good, because you can keep on going around in this loop here. And what we want to do when we recognize all the tokens for a language is you basically get all of these state machines. So like, here's the one for variables, here's the one for numbers, here's the one for the plus. And we've got one down here, which is another trivial one, which is white space, which is just white space. You start off in the white space. And if you see a space, then you're still in white space. What you do is you take all of those state machines and you put a new start state at the beginning. And then you put epsilon transitions, so ones that you're basically free to move along from the start state into this start state from all your individual tokens. And then based on this, you can build a new state machine which represents where you could be at any given time in this specific state machine. So you say like, in the first place, you could be in state S, or you could be in state V1 or N1 or P1 or W1. So you start off building up this table that says like, if you're in our DFA state, big S, you could have been in any of these NFA states. And then you say like, if you see an S, where could you then go to? Well, if you see an S, the only place you could have been and still be valid would be in here. So the state would end up being that you go to the state big A, which corresponds to the NFA state, blah, blah, blah. Basically, it's hugely complex. But if we actually have a look at what this ends up boiling down to, it's effectively like the first character that you see in tokens often determines which state you'll end up going down. And then there's just a series of different transitions that you need to go through to be able to recognize that kind of thing. Like if you see a plus, then in this case, we know it's an operator, but hypothetically, it could also be that plus leaves you in a state where you could either just be about to pass a number or you've just seen a plus. So we can start just encoding these as states like, we're in the white space state. So if we see white space, we stay in there. If we see anything else, bad times. If we see a plus, we're in the, I've seen a plus state. But then if we see a number, we go, oh, I'm in the passing a number state with a numeric like a sign prefix and that kind of thing. So it's actually, although there's like a lot of theory behind this, oftentimes when you actually look at the tokenizing state machine, you're effectively saying like, if I'm in the start state and I see some white space, I'm in the white space state. If I see the plus, I'm in the plus state. If I see a number, I go to the parser number state. If I see a letter, I go to the parser identifier state. And then you say like, oh, if I'm in white space and see white space, I just carry on going, blah, blah, blah. And so what this is representing tokenization as is basically walking through the characters in the input buffer. This is Rust, by the way. Recognizing the characters in the input buffer, and then for each character, you try and see if there is a potential transition you could make. Like, could I, like, if I've seen no characters, can I potentially have a token which contains this current character? And then you just go one by one. And you go, okay, so the next character is now like, I don't know, we're here in the identifier state. And go, okay, so the next character is a 0. Go, okay, that's fine. We'll stay in state D. And then we come back around and the next character is, I don't know, a space. And we go, okay, so I'm in state D, match the character. Is it one of these? No, it isn't. So we go none. And then we effectively break out of the loop by saying, like, if the next state is not anything, then we break. If it was something, we'd basically keep on looping. And then at the end, we look at we can take the string that we've recognized, which is basically we keep track of where we started, where we've got to. That's our string. And based on the state, we can know what our token is. So in this case, it looks like the Lexer is deliberately dropping white space rather than returning white space tokens. But we could just have a switch that says, if you're in state blah, 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 then return like the white space. So the plan is fairly simple. The Lexer just needs to have a buffer of text and it keeps track of the current token and then produces the next token when it's asked for it. So I think we should probably represent that as a class. Just gonna put this over here. I need to have more tea. So, type Lexer. Maybe. Input, which is a string. And we'll say let input buffer or buffer equals string input. All good. The lexical analyzer. This tokenizes the input and exposes the current token. Tokens retrieved by bump. Bump's fine. Bump is kind of like a traditional name for the advanced method in tokenizing, because you're just bumping the pointer. So we have our input text. And we have the API that we want to produce. So we want to say let current is going to be, well, we need this to return some kind of token structure. And for us, we know that the token structure is going to be a string representing the value and some enum representing the token kind, because we know that we're eventually going to want to put those two things into the Firethorn tree. So we might as well return token kind end of file for the time being and the empty string. And this is going to be a case, so we always want this method to return something. token kinds for the language. And type token kind. And then this is just going to be enum, by which I mean union. Grumpy Game Dev told me off last time for calling F# unions enums because they're enums in Rust. Oh well. Retrieve the current token. And then we said there was going to be a bump method at the moment as well, so bump will, well, we can do unimpl, I think. Unimpl. Not yet implemented. Is that what are you upset about? Ah, yes, because this needs to be a member definition, not a let definition. And yeah, we'll need to pull in unimpl from the helpers. All good so far. So we should probably also start some tests for this Lexer. So right now, this Lexer will work correctly if you give it the empty string. So let's go and start there. So we need to store this in tests. And we'll call it Lex. No, that's the search box. Lex tests. So we said if we empty input text always returns end of file. So we can just say let Lexer equals a Lexer over the empty string, and then we can just say assert dot I need to add this to the tests, don't I? Compile. So we want to say assert equal, yeah. For that, I know we want open X unit. Yeah. Then for assert equal, we want to say token kind end file Lexer dot current well. Do we want to model this as an actual record? Well, we can just have it as pair. And we can just put get kind, I guess. Token let kind text equal token and kind first kind. So we check it's the end of file, and then also we can check that it repeated calls to it also return the end of file. And the idea here is that, well, that's gone well, hasn't it? What are you upset about? Okay. Okay, so you were just a little bit confused. I mean, the tests look to be passing. I think we're good. Yeah. Hello. Yeah, thank you. But this isn't the world's most interesting Lexer. So what we want is white space tokens. So we'll do this as theory. And we'll do some inline data. Because we know that there's going to be lots of different kinds of white space. White space returns a white space token. Yes, code, you were so... It really doesn't like these backtick identifiers. Every now and again, I mean, I assume that it's yeah. Reopen, please. And I think it is happier when you do them like this. So white space returns single white space token. So then we'll do let we need like space white space or Lexer equals Lexer space to make our Lexer, and then we'll do assert equal token kind white space Lexer the current kind, and then assert equal end of file. Yes, we wanted to bump here, didn't we? So we might as well include two, and then a call to bump. So this will force us to actually write some stuff because we need no, it's not happy. do I just reopen the editor again? Let's try. That unit test stuff really does something funky to ionize. Yeah, C sharp's not happy, but that's fine. C sharp's regularly not happy. It's opening the info panel, which isn't what I want. Let's go to definition. Definition. Implementation. Show definition preview hover. Doesn't really sound like what I want. Yeah. Not in an F# project. We are in an F# project. Right. I think it's back on track now. Just need the buffer to be closed and reopened. So, can you just... No, you can't. But we can go here and we can put white space in. So I don't need token kind, but they'll at least make the tests pass. But, well, sorry, the tests compile, but it won't make the tests pass. So what we're going to want here is like let current equals none. And then what we can do is we can say if current's going to need to be mutable. We'll do a match current. No. If there is some token, we just return the token. There's no token, then we do current. Yeah, thanks. The test current is, well, we can just start it off as being end of file. What do you upset about? Unit. Okay. Oh, I see. Because it works out that the return value of this match has to match the return value in token. Yeah, well, I mean, you're kind of wrong there. And then we do match again on current. Maybe we should have like let next token equals, and then we do sum next token. Is that right? What I'm trying to do here is only buffer real tokens and then fakes for the end of file. Because but I guess we could just fabricate one end of file token and leave it at that. Show next token. Okay, so current is now still a pair of token, kind, and string. And then bump basically just does current is none to clear out the token. Advance past current token. Try get next token. You want this to be like self try get next token, and then we say we can do a match here, or we can do an option, because if we just return an option here, we can do option default value. And the default value is going to be token, kind, white space, and the empty string. And then we just need incomplete. Why is that expected a with or a token? If no other tokens not 100% sure about this API, to be honest. Could well be that we just want it to always return something, and then we could do some next token thing like we were just doing, and have effectively the check for whether or not we need to return this wants to be end of file. Whether we return end of file as being, is that, what are you upset about that? Member bump. He really thinks there's a problem there, but I don't know what it is. Also, what's going on in the Lex tests? Yeah. Okay, so you're happy. Incomplete structured construct at or before this point. Really does think. Oh, is it saying, oh... Oh. That's what it was saying. It was complaining that I'd put a match in a place that I didn't need a match. So. What we need now is we need a try get next token to be implemented. So what we want to say is does not define the field, constructor, or member. I mean, it kind of looks like it does, though. Oh, it's because I broke it down here by removing the none. Okay. One test failed. That's an advance. So what we're going to do is walk through this buffer, which is our string, character by character. So let mutable ts 0. And then what we say is for char in buffer. Do I want to like slice this? Can I slice this? I don't want a substring because that's gonna. Can I do as span? Can I use spans in up? I would like to. String slice sharp. Because otherwise there's going to be an awful lot of slicing F-sharp lists and arrays. It looks like you use the indexing syntax with a range Let's give it a go. So that would be ts dot dot. And then we do let so for each so let state equals Lexer state. We'll just call it Lex state start. We'll create a type for this. Okay, so I need to do the type up at the top. Do I? Can I not have nested types? Yeah, this. No need to states in our Lexer state machine. So we want to do this thing where we effectively look at the transition for each character. So we do match state to match over the current state. And if we're in the start state, then we do match character with, and then in this case, you're wanting to represent anything when is white space. What's that? Char is white space. C, something like that. So if that is true, we'll say this is starting to drift off to the right. I'm starting to think some of this is needing to be extracted. Some Lex state white space. Anything else? We'll say none for the time being. Should be it. And then we can say, oh, we just want to say state or next state. And then we can say match next state with some next. And if that happens, we set a state to be the next state and non break from the loop. Now, what are you upset about? Lex state does not have white space. Okay, yeah. Char. Is it just C is white space? Nope. Do I need to open system? I think I need an open system here. When char is white space, Come on. We had this in the other Lexer. So here we are. Char is white space. Okay. Char is white space. C. So that bit works. And then we can fix the not having a Lexer state for white space. Just putting one in here. What about the next bit? State. State's not mutable, is what it's saying. Cool. And, well, it's going to say that here it's saying we haven't covered white space. We haven't. We just stay in the white space state until we stop seeing white space. How do I break from a for loop? Done? No. So we got transitions, and then we want to say token end equals token end plus 1, because we've just advanced over one character. Or break, maybe? We have to make this into like a while not done loop. I think we might need to. I guess we can do that. I'll manage to do it. Mutable finished. False. Then we can do non makes finished. True. That. We do. Let's see equals buffer. We want to get the chart at the token end because that's our current pointer. Okay, that should work. And then what we want to do is match the state that we are in. And this is where we work out what we've managed to recognize. If we're in the start state, then technically this should be well, yeah, for the time being, we can have this return none because we weren't able to make any progress. Otherwise, white space. We want it to return some. Can I do like a return here? Okay. So if we got white space, you want to return some of token kind white space, and this needs to be buffer TST. Would you let token value equals that? Then we can do TS equals T. No, like this. What are you upset about? Value is not a function. Okay. It's looking pretty promising. And it's taking this long to build, so can't be catastrophically broken. Oh, that's unfortunate. Why have our tests failed? As soon as there's two, it'll be the Lexer ones. Input. Index was outside the bounds of array. Okay. So whenever we've gone through this, token end will always point to the character. The token end will always point to the next character that we weren't able to recognize. You could make this complex where we have to work out here whether or not token end is valid or not. But I think what I'm going to do is just put another variable in here. So we'll say like let mutable next equals token start. And we'll say token end equals next for the time being. And then what happens is whenever we do this, we say we look at the next. And then if we mutate it, we say token end is next. Let's just do this token start. Bit of renaming because this is getting confusing. Token end, and we have all these characters, you might as well just use them. So next character is token start, token end equals next character, finished is false. We take the next character from the buffer, switch over it to get the transition to the next state. We store the next state, and then we set the token end to next char. Because that's the one we just looked at. And we set token as we set next char to be next char plus 1. So next char, which really should be current. So we look from the token start to the current character. That looks a little bit better. Goes the testing. So now I'm not in the... I don't understand. So my next and previous is scrolling the top. I've installed some Emacs mode stuff here. 2 fails again. Try get next token. I wonder if this is just the case where token start do we need to do and current char less than buffer so that what we're not considering is reading past the end of the buffer, just because when it's empty we won't be finished. The state will be start, but the current character, which is 0, won't be a valid index into the array because the array has no elements. And the same thing when we've read our white space, we'll keep on reading our white space. That's potentially more promising. No. Returns a single white space token. And it's failing at end of file. So try get next token, you'd expect to return none. Well, let's change this to be just get next token. Then this is some next token, and then we return token. Then we can just get rid of the try there. And in here, we just do token kind end of file, token kind white space. Don't even need to stub out that because you could just do the match to get the kind. Well, that's gone badly. How about we just indent you instead? Yeah. And then token value kind. Then we just return the pair kind token value. that shouldn't have made any difference to what we're seeing as a failure, but it should make thinking about it easier. So it's calling bump, and then it's expecting end of file. So it's going to go into Lexer current. Current is then going to see none, is it though? I mean, it should do. So it's going to then call next token. So get next token is going to not be finished, but the current character. I think I know what's happening here. We're not. So current character is now the first character that we token start equals token end. Just token start just needs to equal current character instead. I don't think we actually had like a token end. And current being different. So maybe it's just, I'm not sure if token value is going to be different. Broken here. Seems like that's fixed it though. Right. So let's stage what we've got. So we now have legacy syntax. We have the Lexer and the Lex tests. Changes to compiler services, changes to the tests. Can we get rid of current character? Because it looks like well, started snowing. We can assert, can't we? Assert equal space Lexer current get value. Get value from a token is let the kind and the value token value. This can be a document. Grab the kind, the value from this from a syntax token pair. Whoops. Is this going to fail the test now? Because I'm not sure whether or not the token that we're learning here is ending up being just the empty string. No, it looks like the token we're returning is correct. I guess it must be to do with the slicing behavior. I guess that Rust slice is exclusive and maybe R slice is inclusive. Why would that be? Just the way that indices are working? I guess. Anyway, let's put some more tests for white space. How about 2 spaces? Or how about a tab and then a space and then a tab? And how about like a new line? And how about carriage return new line? How about just a carriage return? I think you get the idea. I don't know right now whether or not we're going to want these to be different kinds of white space, but we'll leave it. Kind of looks like probably enough test cases. I'm also wondering whether or not we could just make this white space return a single token to just be like Lexer Lex single token and just have the kind in here. Because the Lex is going to have a whole bunch of different token kinds we need to recognize. This Lexer only has one token look ahead as well, which I guess is fine. We'll see when we actually end up starting to pass some things. So I'll change this to Lex single token, and we'll take a space, which is actually going to be token, and we'll take a kind, which is going to be kind. Then we could say token, and then instead of doing white space, we can kind, I guess. That's gonna be token, and we expect end of file at the end. That kind of makes sense. And then all of these, we're gonna need token kind white space. Oof, it's not happy. It's because it's not really an enum. Can I do enum? Token kind? Is that a thing? Or can I... That's unfortunate. You'd have to make all of them numbers. Ah, hey, it's Grumpy Game Dev again. It's expecting me to type the parameter list for my test. I don't know how old this comment is. Oh, black hat. Okay, yeah, so, yeah. I'm pretty confident, though, that it was because it was a union. It says not a very constant expression for a custom attribute. So I'm pretty sure we can get around that. by making token kind an enum so that you can put it, because you can't serialize a union into an attribute. But that's made it happier. It's just unfortunate that I'm going to have to manually do that. Grumpy Gav says, oh, so namespace, then you just leave it as white space. Are you talking about the fact that I don't need to token kind end of file most of these things? I could just call it token kind white space. I mean, yes, but also I kind of like the slightly more explicit always putting the thing on when we've got white space in both these enums. So sorry, this is actually still a union, this is an enum. I'm going to call them both enums because I'm rust. I guess we need to start thinking about other tokens. So this is a Lisp. So open brace, I guess. Oh, you did not enjoy that. That looks correct. So we should probably have end of file last, shouldn't we? So open brace. So to open brace, we'll want to have a Lexer state for it as well. Yeah. I'm having to think about this because we might actually just want Grumpy says in the US we have different names for, well, yes, we have different names in the UK as well. So in the UK, I would call this a bracket, I would call this a square bracket, and I would call this a curly bracket. But I don't know how much of that is like UK specific, where I grew up in the UK specific. Yeah. So I guess we can call it open bracket because the curlies are more what I would think of as being braces. So let's just sort this out. Open bracket. It's just more characters to type and therefore more typos to make. Grumpy says they are parentheses, brackets, and braces. Well, that explains why I think that the curly brackets are called braces. And I guess they kind of look like they should be called braces. But you are potentially wrong about other things. But it's interesting what, like, where allegedly we're speaking the same language and we just have completely different names for so many different things. Naming things is hard, apparently. I read somewhere one time that apparently a lot of the dialects and stuff from the US English is actually not that US English is diverged from British English, but more the other way around. Like US English is in some ways a more accurate representation of the English that was spoken like 200 years ago, because whereas UK English has moved on in different ways, but I don't know how biased that article was. At least I think in terms of accent and things. Parsing of things. So we could put a lex state for open bracket. And let's just do that and show how it would work. So lex state for open bracket is, we'd say, like in the start state, if we saw the character open bracket, then we would go to some lex state open bracket. And then in here, we'd say if we saw an open bracket, then anything we saw becomes a none, because there is no transition out of open bracket. Once you've seen one, that's it. And then down here, when we do the state, we'd do, if we saw open bracket, we'd say token kind open bracket. All very well. And so now our test should pass if the test actually compiled, which it doesn't because it's still called brace here. Yeah. That thing. How about now? No, we don't want to debug it. So that would work, but there are a lot of characters in our grammar which end as a single kind of character token. So I think it probably makes sense to say single or simple token and have a token kind in here, and then that's messy. That's not how you do that. Of token kind, and then in here we say if we see an open bracket of anything, which is going to be simple token, we do lex state simple token kind open bracket like this, and then down here we can just do simple token of type T, return the type T. So we basically use our Lexer state to store the current, like the kind for what we're looking at. So that then should mean that we can start adding things like close brackets, quite easily, because close brackets would just be in the start state. If we saw a closed bracket, then we go to the simple token for tokens type kind close bracket. And then go to the tests, we should be able to just do the same thing. And now you can make white space simple token, simple token, simple token, because that is silly. White space pipe to simple token, pipe to simple token. I mean, I appreciate it sounds like a silly idea, but don't fully understand what you're talking about. Simple token is a token kind. So you could put a token kind white space inside a simple token, but you wouldn't then be able to wrap again. Yeah. Yeah, so that's, yeah, that works. What other tokens do we have? So yeah, simple tokens, we've got the quotes, we've got the unquotes, unquote spicing and dot. So they would all be simple tokens. Think we'll just do that for the time being, because all the rest of the stuff where it gets into identifiers gets a bit more complex. Yeah, so I'm just going to copy these because these are like funky quote characters. And I believe so that and this are both the same kind of quote. Which would be some next state, simple token, token kind, quote. Think. And then, because I remember we had problems with the examples using one kind of tick and we'd expected the other one. So then this is unquotes and unquote stuff like that, which is just going to be a token kind of its own. Next state, simple token, token kind, unquote. And then this one is the dot. Next state. But I don't think we can just use dot there. So what do we have? Quote was the next one, and then unquote and dot. I don't think we can just do dot because dot will end up like you can have dot on its own. We'll put it in as a test for the time being because it should still work. Token kind dot. And we also had quote being that and quote being this. And that was unquote. So they should all still pass. But the problem is that if we see another anything that could be in an identifier after dot, then it's actually an identifier, not a dot, because dots are only dots if you see them on their own. And we can see that in our current syntax. We have the tests for that. Yeah, so like these are all identifiers, and then that bit rude. Oh, it's just the spurious error that sometimes happens. These are all identifiers, like 2 dots, 3 dots. In fact, this would be it. These would be a good source of more tests later on. It's like what went wrong. Actual end of file. Why? Because it's not that quote. This is exactly what I was talking about. We should probably support all three, and just having a look at the yeah, I don't think that the single quote character is used elsewhere, so we could just support that for the time being. Like it's not used for characters because characters use that funky escape. Yeah. Go on, we'll support it. Which is going to be escaped, I guess. Then in the tests, we want another. These. The Grim Gamer says, but that does lead to the question, is white space a token kind or the other thing? So, are they interchangeable or are they basically buckets for strings? So the idea here is that our tokens are just going to be strings, well, pairs of strings and some kind. And at the end of the day, we're going to end up putting them all into a tree because we're trying to do like lossless parsing here. So inside this Lexer, what we've got is a buffer for the current text, state about what our current token is, and then we have this get next token method, which basically walks through the characters running a simple state machine. So the state machine starts with the state being start. So Lex state is like a state machine state representing how we're walking through parsing a single token. And then as we move through the state machine, so it's like you can tell it's a state machine because it's got like a 2-level match. So we match on the current state, then we match on the thing that we're looking at to decide whether or not we've got to transition to a new state. And so we're using an option where we return some if there's a state to move to, or none if there's no further transitions, and then we break out of the loop when we find no further transitions. And wrap it up as a token. So yeah, that's it. And I did show an example earlier of the kind of thing that we're trying to mimic is this. So this is like an actual formal state machine for parsing a simpler set of tokens, where you have like the state machine for each token. Like this one's an ID, where we say we expect a character and then a character or a digit, and then this one's digit or digit, blah blah blah, and then we have Epsilon transitions. But basically, I pointed out the observation that you can pretty much tell from the first character usually what kind of thing you're going to parse. So you can just do like a few named states where you see like, oh, we're looking at white space, we're looking at this case and say, oh, we're looking at a simple token plus, we're looking at digits, and you can just keep on in the digit state if you see digits. You don't need to go and actually do the formal transition diagrams. So yeah, the Lex state and the token kinds aren't interchangeable, because we're going to end up with some states where like we're partway through parsing, well, partway through lexing something like a comment. So let's go do comments next. That'll probably illustrate it. So if we say tokens lex state is well, what's the comment character? Yeah, comment, single line comment. And we can have a token kind for comment as well. And we'll say just the single comment character is a comment. And then also like the comment character followed by anything is also a comment. And the comment character a few times is still a comment. Yeah, that'll work. Just trying to think about whether or not new lines are considered part of the comment. I think technically they're not. Like the trailing new line, you should expect this, but this doesn't have a new line, so I think we're good there. Lex. So we need to add a new one in here for how to get to the comment first, which I guess is if we see this, we go to some lex state single line comment. Yeah, that's it. And then in here we say if we are in the single line comment, then we match the current character. And basically, if it's either a carriage return or a new line, done. Otherwise, single line comment. And we need to return it as a kind down here. Yeah, I know. Token kind comment. And we can also like have a multi-line comment state where we say like, oh, I've seen a multi-line comment, but I'm this far nested. And we can use the state machine states to kind of like allow for arbitrary depth of comments. How would we do that? because multi-line comments in Scheme is a bit interesting. We have this like hash, so we'd have to say like I've seen a hash, and then if you see a bar, you'd like, okay, I'm in a multi-line comment. I guess my comment tests didn't go well. Match cases were incomplete. Okay, well, that makes kind of sense. Yeah, but single line comment is there. Yeah, so multi-line comments is like looking for / and stuff in C# or any C style language like Java and that kind of thing. But I think this is just out of date, isn't it? I think I just fixed it up afterwards. So we can have like scene hash is the state, and then we can see like in multi-line. And then we also have like in multi-line scene hash. And in this case, like if we've just seen a hash, we actually have oh yeah, F# uses the curly bracket and star like that. It's an interesting choice, and I guess it kind of looks a little bit like it's quotation, so I get where it's coming from, but I do kind of prefer doing just several single line comments, especially when you're doing like dot comments and stuff like that. Just looks cleaner than having closing comments. So yeah, we'll have scene hash and then in multi-line scene hash. Where we can either go back into multi-line or not, depending on like, so the way this would look is like if we talk about the F# work case, we're looking at wow, that was a mess. If we are here, we'd say like, oh, we've seen a bracket, then we're like, oh, we're in a multi-line comment, and we're in a multi-line comment, and then we go, oh, we've seen a star. Okay, so it could be about to be the close of the multi-line comment. Oh no, we're just in the multi-line comment. Oh, I've seen a star again. Oh, now we've finished a multi-line comment. That's the plan. So we'll do that. So in here, we say if we see a hash, and it's called scene hash because there are other things that could start with a hash. And then we say, if we've seen a hash, and then we see a bar, we are in a multi-line comment. Otherwise, well, we'll see none. There's no transition. If we are in a multi-line, then we match the character if it is hash, sorry, bar, because this is the other way around. We say, I've lost track of which way around the comment is now. Yeah, hash, bar. Oh, so we need it to be like in multi-line scene bar, but whatever. Then we'll say some Lex state in multi-line scene bar. And anything else, we say, okay, we're just some next state in multi-line. We just keep on in the multi-line for anything else. And then if we are in multi-line and we've seen a bar, we say match the character. If it is a hash, we know that we finished the comment. So it's some Lex state. I think this must be none because this is where we have no further transition. So if we've seen this, I think, oh no, we need there to be like a multi-line done. Because otherwise we're not going to actually skip over this character. And then anything else, we just go back to the sum Lex state in multi-line. Because it was just that we'd seen a bar and that was it, and we're carrying on. Yeah, so we want that. It needs to have like a multi-line done. Okay, that'll cover some of it. So which ones do we want to say? I'm just going to put all these simple accepting states at the bottom. So like simple token or multi-line done. Just simple accepting states. Then in here, we want to say if we were in multi-line done, then we say token kind comment. We can put that in this case as well, I guess. And anything else, we actually want there to be like a token kind error, which is that we've seen a token, but it's malformed in some way. Because this could be like, oh, you've started a comment, but you haven't finished it. Yeah, I guess we just want to have a token kind error here. Which can just be a high number. Let's see about doing some tests for those. So if we see a hash and then a bar and then another bar and then a hash, that is a comment. if we see a hash and then anything, that is a comment. If we see a hash and then some bars, that's still a comment. Then if we see a hash and open and it's not so unterminated, then that's an error. And the same thing if you're missing just the hash. The same thing if you do just the hash and nothing else. That. How many of those are going to pass? With block comments and uncomment keyboard shortcuts, the multi-line comment sees much less use. Yeah, well, it's interesting because I've got some Emacs mode installed at the moment, and because this is Visual Studio Code, but Emacs is my preferred editor. If I do that, it does comment using the multi-line comment syntax. You can go ahead and put a multi-line string in your line data as well. Inline data. Oh, yes, for an actual multi-line comment. What does a raw multi-line string look like in? Does that work? Can I just put a new line in it? Yes. It kind of looks neater if you just put it like that. What? No. It's already quite a lot of snow now. Yeah, you just hit enter. Well, I mean, I think it looks neater with the character escape. And bar and hash do next, which is where we're going next. With if these tests all pass, which it looks like they just did. So if we have a comment, we can also say like hash and then another hash. So you can say double commented. Still getting the hang of this. The subtly different keyboard layout on Linux versus Mac always gets me. Yeah, so this should nest correctly. And at the moment, this is going to fail. But our Lexer state should make it a fairly simple thing. Because up here, we can say we are why did that not? Oh, it did. Yeah, we got one failure because we were expecting to see this whole thing, but we actually stopped parsing it, we stopped lexing it here. And I think the solution to this is we say, if we're in a multi-line comment, we are actually in a multi-line comment of some depth. And if we're in a multi-line and we've seen a bar, we're also in the common of that depth. And I guess we can also have in multi-line scene hash of depth int. So that's when you're about to go deeper into a comment. So transitions wise, we say like if we have seen a hash, we're in a multi-line of depth 1. Or yeah, go on. And if we're in a multi-line of depth n, and we see anything, we're in a multi-line of depth n. I've seen bar at depth n. We're in multi-line at depth n. And the two cases we need to handle are when we've seen a bar here, we need to make a decision between if n is greater than 1, then we were actually just in a multi-line 1 further out. What are you upset about? You're upset because it needs to be like that. And if we're in a multi-line and we in a multi-line and we see a hash, we need to go into multi-line scene hash. At the current depth. And then when we see a bar in the multi-line scene hash, we go deeper. In multi-line and +1. Anything else here, then we just go back to in multi-line. That might work. At what point do we decide that the function is too long? I would say it's not to do with the length of the function, it's to do with the complexity of the function. That means it needs to be broken out. I'm quite happy to have this really big, long match statement. What I'm kind of not happy about is the fact that there's this big, long match statement and we've got all of the machinery around looping and that kind of thing. So I think the match statement should be extracted into like next transition, where we say, here's the current state, here's the current character, where should I go? And the looping over the characters that decides the outer machinery. Which I think let's do that now. You've guilt tripped me into this. Self.next transition state character. And then we do member self next, which is going to take a state and character. Where? I think that's right. Yeah. Then this needs self. And we probably want to reformat this whole thing. It's always interesting to find out what Phantomas ends up deal with this. I have lovely tests. I have the tests exist and they look nice because what's the type? Oh yeah. Tests look nice because I've installed a new theme. I mean, also, the other thing that we do have is up here, we have this big folder, spec, which is full of scheme. And at some point, when we get this Lexer up and running and work on the parser, we'll be working to parse those scheme files the same way that we used to parse them, just better with lossless syntax. That's the plan. So as this gets more complex, hopefully it should actually get better depth of testing as well. So get the next transition, if any, for the current state, and this returns some transition exists. On, if not. I think that's good. It's not true anymore. If no further tokens are available, then token kind and that basically means that you, every time you try and read more tokens, if we've got to the end, it just keeps on returning end of file, because that just makes writing the parser a lot easier. Rather than having to deal with like optional existence of tokens and things like that, you can always say like, oh, peek at the token, and if it's not the same, rather than having to say like peek at the token, and then if it is a token and blah blah blah. I think that should work. So we've got single line comments, multi-line comments. What other kinds of tokens do we want? So let's go have a look at some scheme. Identifiers are going to be the interesting one, because identifiers kind of seem simple most of the time that you write them, but the actual rules for them are a nightmare. Most people don't write identifiers taking into account all the rules, but like one of the cases, like here, a minus sign on its own It's an identifier. But if I do -1, then that's a number. But then if I do like -A1, that's an identifier. So interesting. I guess we can do digits. Well, numbers have a whole grammar associated with them. I think identifiers are actually simpler to parse than numbers even. But what can we do here? I think we should probably add like an error token state for everything else, because at the moment if I write something that we don't recognize, the tests, let's prove this out. If I write something that we don't currently support, like an identifier, what it's going to do is it's immediately going to say, oh, there's no transitions. And so it's going to say token kind end of file. But then it's going to keep on doing end of file. But really, we want that to be like identifier. So if I run this test, we should get expected error, but was end of file. Graham says, so the space is the delimiter. It depends. So a minus sign and a space and then a 1 is 2 tokens, whereas a minus sign and a 1 is a single token. It looks like this. We have the idea of delimiters, intraline white space, and something it later on calls like atmosphere in a very extravagant way. So a delimiter is either white space or a vertical line or opening and closing brackets, blah, blah, blah. Because these are the kinds of things that could signal a new token starting. Because like you're starting a form, or you're starting a string, or you're starting a comment. The vertical line is because you're going to start an identifier. And then like the identifiers are either initial or followed by subsequent. A vertical line, some symbol elements or vertical line, because you can quote identifiers by putting lines around them. Anything goes in the middle, including the ability to like explicitly encode Unicode scalar values, and then this whole thing called peculiar identifiers, which covers the cases that I've just been chatting about, where a peculiar identifier is like, effectively, if you see a plus or a minus, you go into this like explicit sign state. And then from there, you may go into, like, if you see digits, then you may go into parsing a number. If you see an alphanumeric, then you can parse it as an identifier. And then there's actually these special things where, like, if you put, like, technically a plus, and then these aren't digits, so that's fine. And then dot, which is also valid in a identifier, and then a 0. So that is an identifier according to the identifiers grammar, because it's an explicit sign, a sign subsequent, which is, any character that doesn't make it a number, and then anything that goes into an identifier, which is just general subsequence. But then, like, you just have to just explicitly check to see if it's any one of those, because if it is, then it's infinity. Or a nan. Interestingly, you can't just do like int.0. You have to give it plus or a minus sign. And I said like the grammar for numbers is more complex. So this set of productions, which are actually then generic over the radix, so like exists because you can have like complex numbers and real numbers and all the rest of these kind of things in any radix, and then you also have a special set of extra special ways of writing decimal numbers. It's interesting. At least the radix is actually fairly sensible. Where was I? How do we pass an identifier? I guess we can pass anything for peculiar identifiers quite easily. Because peculiar identifiers are just initials followed by subsequents. So we can do this just by having an identifier state that we go into when we see any of the initial and then stay into when we see subsequents. So subsequents, basically initial or digits. An initial is a letter or special initial, which is this list of things. Can I copy it? Actually, what was the second error there? Oh, I just did the source file of fib. Can't be doing that. Oh, it's going to write a new line on save. I just want to get out of this. Edit it with something else. Update that test. Update that test. So we're using snapshot testing for the integration tests. The snapshot doesn't have the new line at the end. So we're getting back a different set of tokens in the path tree. So identifier as a state, identifier as a token kind, I guess. Um, 7? Yeah, 1. Great. And then in the start state, if we see any one of these, well, actually you can do see when when char is alphabetic, yeah. What do they call it? Letter. Or any of the things that I copied. They're still not in the clipboard anymore. Time for some multi-line, multi-cursor action. So, oh, no. that, and then that, and then that. I can't believe I've pulled that off. And this. How is Phantomus going to wrap this? So we get to an identifier. And when we are in an identifier, what's a special subsequent? Do we want to... Let's put these sets of characters somewhere. Cause or we want to say like or array contains special initial and then put these things here, which means more multi-cursor to undo the previous multi-cursor. Too far. That looks better. That doesn't look better though. Can I do 2 bars for that all? That's not an array. No. I could do string contains, I guess. Find. Ooh. Yes, you're right, Graham. This is what we want. We want special initial to be a set. So we want to do just gonna do this. It takes more concentration than I thought it was going to. Then trying to talk made it break. What are you upset about? Value is not a function and cannot be applied. Well, I didn't try to apply it, did I? Oh, yes. And then we can do set contains. That sounds better. So down here we can say in identifier, then if the character is letter or digit or special, what did they call them? There's a special name for the subsequents. So initial or subsequent, where subsequent was either an initial or a digit or a special subsequent. And special subsequent where do we use that elsewhere? Is it just used here? Because we can just make special subsequent a set. Yeah, those make special subsequent a set as well. Simple, what was it called? Special initial set some X state identifier. We are still in an identifier. Sure, that's what did you see? And we need to define the set for the subsequent. Which is going to be this, an explicit sign, which is either a plus or a minus, or a dot, or an at, whatever this is called. At. Set. What are you unhappy about? The fact that I've just not given you a character to check for. Fair enough. Let them race. Crimkender says, I'm not sure how many peculiar or special things I like in a language. Well, yeah, you're not wrong. Also, people say Lisp is easy to pass. But I think the thing is that it's easy for you to look at it and go, oh, yes, well, clearly that's an identifier, or clearly that's a number, or whatever. But it's like, not everything having to be white space delimited and all the rest of that stuff. And white space affecting things in ways that you don't expect. Like, in F sharp, if I... that was loud. But yeah, in F sharp, if I write n minus 1, then that is the token for the identifier n, and then the token for the minus, and then the token for 1. And if I write something like n minus 1, that's... God damn it, F sharp, you don't do this the proper way. If I'm in C sharp, if I'm in C sharp and I write something like n minus 1, that's 3 characters. And if I write n minus 1, that is still 3 separate things. That's the token, that's the token, that's the token. So like when I write something like minus 1, this isn't a literal value for minus 1. It's the token for minus and then the token for 1, which when the parser sees it, because it's not seen an expression already, it knows that this minus is a prefix operator. So this minus 1 becomes the prefix operator expression. So if you have a look at the way that this semantic highlighting is working here, if I press expand region here, it expands just to the 1 because that's the next semantic thing. And then if I expand it again, we end up with the minus and the 1 because they are 2 logically separate things. It looks like F sharp doesn't do it like that, which is interesting. So if I write minus 1 in F sharp, see, that still thinks it's 2 things. I wonder how much of this is down to bad syntax highlighting. I know that the C sharp example I just showed you, the tokens are coming from their semantic tokens API on Roslyn, which basically it passes the file and then tells you the tokens, which is part of the reason why I'm actually trying to do this, is that I want to support semantic tokens as well. Whereas I'm not sure if the F sharp parser does it in quite the same way. I know it doesn't do the whole full fidelity syntax trees the same way that Roslyn does. It has a representation that's a lot more like the current Feersum tree, where it's got a bunch of different union types and it drops information about stuff because it's constructing an abstract syntax tree rather than a lossless syntax tree, which is fine. It's fine, but yeah. So I think this should be an identifier now. Should be things like foo 1, 2, 3, and That should be a single identifier. I don't need to go overboard because these are going to get tested by the identifiers test later. But we don't support peculiar identifiers so far. And we don't support ones that start with a dot. What else can we do? We can do those like that's an identifier, I think. Is it in special initial? Yes, it is. The full test suite that we'll expand it to later does contain like all of these different characters and all of the combinations you'd expect. And Grumpy says in F sharp the operation is actually applying the binary minus to n and 1. Interesting. Well, we can find out. Brace yourselves. If I do -1 and then I do go to definition, what do we get? There's some magic. Something's not quite right. There's a lot of things where you can actually go to definition and it does just work. So I think this should be some forms of identifier that we now parse. Let's stage what we've got. So yeah, there's that change the end file. Let's actually just stage that as a separate thing. We commit that to fix up white space in spec fib. Then we can just stage everything. And this is initial Lexer. This Lexer runs simple state machine to recognize tokens. Not all tokens currently supported. This is not really Emacs, so it doesn't do the wrapping for me. What a shame. But it's so close. This is some extension that mimics Magit, which is just one of the best things. And without actually having to open that to Emacs to use that, it's so nice. Let f equals -1 is a partial application of course it is. Anyway, I trust you. It is just the kind of like slightly counterintuitive thing that would happen. So what I think is, at the moment we have these syntax tests which check the current parser. We don't have a parser yet, so we can't really deal with that. But what we could do is, I think there's a bit here where we, or is it the spec test? Like we have, yeah, executable specs, library specs. And somewhere here we actually just pass all of the tests. Get parse tests data. Excellent. So I reckon we should have like a test in here that just runs the tokenizer over things and fails if any of the tokens are error. I guess. And then this will this will let us know what bits of syntax we need to concentrate on being able to parse. Test new Lexer. Yes. And we'll use the same member data as this. And we're going to say let Lexer equals Lexer. Let file equals, or source text equals file read all text. And then we create a Lexer for that source text. And then we'll say well, if we're going to write a while loop, we can do assert not equal token kind. We're going to really need to bring that into scope. Token kind error. Kind. Can I put a message here as well? Is it just assert true that you can do that with? Yeah. So set true kind doesn't equal token kind error. And then we can do, I know. Need to add a done. Do we? This is going to be token start is less than buffer length. Not. Check if there are more tokens. That needs to be a property, I think. Enough to trick Ironide into making it. Grumpy says, "Have you tried the NuGet package Shoodly?" Yeah, I've had a look at some of the assertion libraries for F#, but I've never like started using any of them in anger. I'm still just XUnit basic, and a lot of the more complex testing that we do in this project is just using that should match snapshot from Snapper, where we just create snapshot tests instead. I really would like to improve some of the assertions, but when I'm at work, we just use plain XUnit assertions, and though that's just in C#. Is that the one where you could do like, yeah, so X should be 1, yeah, that kind of thing. I mean, it makes sense. It's not really the idiom that I'm used to, I guess, but I should try it because you never know. So the question is, what failures will we get? What? You what, mate? I mean, it does. That one might. Oh, it does. Right. Got some errors. Mainly because it's not able to open any of the files because I've done a bad job. Yeah. Yeah, I get it. No need to repeatedly So if we do this instead. This will be a lot more interesting. It's more easy to understand than assert.equal or whatever. I saw someone use it, got infected, showed somebody at work, infected them. Sounds pretty contagious. I mean, it's going to be something I'm going to have to tinker with off stream, I think, and decide what I feel about it. There's a certain amount of like just uncomfortable annoyance that you're capable of putting up with when you're in the middle of solving another problem and you know how to do a certain thing a certain way. It's not really the top of the priority list. Saying that, I did just spend like 2 days carefully crafting Emacs to make it, carefully crafting Visual Studio Code to make it work as close to the Emacs that I've got as possible, including all of the custom key bindings I had in Emacs, porting them over to VS Code so that things like the multi-cursors use the key bindings I was expecting them to use. At what point do we stop and admit that maybe this is not making any progress and the test's deadlocked? Yeah. So I reckon this is down to that error token stuff we talked about, and then probably just didn't get round to implementing. Which was, if we were in the start state and saw anything we don't recognize, we return none, when really we should accept it. As an error. And that'll get mapped through to token kind error, so we're all good. And then next state needs to also handle error. So when we move into the error state, we should move out of it. It's effectively a simple accepting state. Now maybe the tests will not just sit there doing nothing. Is Lexer mutable or immutable? Lexer is, yeah, this is only semi-functional programming here. So Lexer it's got this mutable state for the token start and current. I was considering making the Lexer just a function that returned an enumerable, just using something like that. But yeah, the idea is that we hide the mutability in the Lexer, and then you just interact with the current and the bump. When I get to the parser, that's going to be the interesting thing, because I don't know whether or not I want parse states to like appear immutable and you have to create a new parse state to move the parser on, which would allow us to backtrack the parser, or if I'm just going to do the same thing of, because it would be quite convenient to have the parser just have a Lexer, have a token builder, a node builder, and have a list of errors, and then as it moves through the file, it takes stuff out of the Lexer, puts it into the node builder to build up the tree, and then builds up its list of errors. We'll see how we go. If this worked though, yeah, it's still not advancing. Why though? Again, could this be if we're in the start state, we're saying move to the end of file, but that means that we found no transition from the start state. Really? I think here we're going to say if self.done, then it's the end of file. Otherwise, it's an error. I could actually just inform that document there. Otherwise, we're going to have to attach debugger to this if I can't work out what the hell's going on. I've not tried debugging since I installed everything. Be very interesting to find out how it works. I've also not tried it in this new theme. It'll be hopefully pretty funky. Evaluate lambdas, evaluate built-ins. Really feels like we're deadlocking. So identifiers aren't working. What did I break? Should be some special case identifier, right? And then when we're in an identifier, if it's a less raw digit, I keep on in identifier. Look on the built-ins again. And is it this? Is this the Oh, it's not very flaky, it just flat out fails. Grumpy says off Sunday, adulting to do. Good luck. And I'm not sure whether or not there's going to be much left in him because I'm getting pretty hungry now. And it is past lunchtime. So I mean, yes, it is definitely that test. Let's fix these other tests and then we can dig into the other one at another time. It was maybe right. Kind 7. Expected identifier actual error. Okay. F foo. It's almost like it's never getting into the identifier state. I'm just going to make this back into token kind end of file because I'm pretty certain that the error catch-all in the other one is going to make sure that we'd only still be in the start state if we'd failed to move on, which would only be there was nothing for us to have consumed. Special initial, special subsequent. We're in the start state. If we just do that, does that work? I mean, I'd hope it does. Still building. Got unlucky. There's a race condition in the build because we try and build the compiler twice. I've not worked out how to fix it yet. So we got some failures, which we'd expect because the actual initial stuff. But why is that not coming back as identifier? Why is it coming back as error? I know what it is. I know what it is. It's not that we're not ending up in the state identifier. It's that when we finish, if we get next token, we go through the state, blah, 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 but we don't actually say, I'm going to put that in here. So we need to do like identifier is token identifier. But I guess we should probably just do list all of these states. So if that says scene hash or in multi-line or in multi-line scene hash or in multi-line scene bar. Okay. In multi-line scene hash. I thought I just did a rename symbol on you. Apparently not very well. What about the next problem? Error may indicate a case not covered. How about that? I like them. No further comments. Good. And That seems to have fixed those Lexer tasks, which is good. So now getting a back identifier. So token start. Is that right? Are we just like going through all the file and then getting stuck at the end? Is that why we're ending up with I don't know. Anyway, let's stage what we have and call it a day. So what have we changed? We now, well, fixed up that typo. Added the done. We've got the identifier token. We've got the error. And we've got this flaky task, which I'll leave. Pass identifier tokens. Picks up identifier parsing and stop using catch for errors because that was a bad thing. And that's it. So thanks for watching, and I will see you next time when hopefully I will have finished out the Lexer so we are capable of recognizing all of the different tokens that we need to be able to parse it, and we can move on to actually building a parser which will produce a syntax tree. And if that all works, we're well on the way to getting the compiler back to the same state that it was before we did all of this investigation. So thanks for watching, and I'll see you next time.